This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Thanks, John. Good afternoon. It's really a pleasure to be here, and fascinating discussion so far from the first keynote and the talk we have after that, and the session before this one, the panel before this one. So I hope that you enjoyed them as much as I did, especially the critical material session. This is really very important for what we're talking about today. Our session is in solid-state lighting, and we'll address important issues in our pursuit for energy efficiency. I think John Bowers, in one of his talks and in the pamphlet that you get when you registered, talked about lighting consumes 22% of all the US electricity, a very large number. And the Department of Energy estimates that widespread adoption of LEDs can save us a lot. I was really impressed when I saw the number 46%, if we can do it. I personally was very fortunate to see the very first white paper that was written in the late 80s by two visionary people at Hewlett-Packard at that time, Roland Heitz and Fred Kish. They wrote a white paper, and I reviewed it for them, that talked about solid-state lighting, and it was very early. Many people did not take them seriously, but they really proved right in their vision. It's taking a little longer, but it's happening. And today we'll find out about the opportunities and the challenges that we are facing in this area. So again, impressive performance. And today I have the pleasure to have 4 panelists with me. In the same order that we'll give the presentation. We'll start with Jim Ibbotson. He is from Cree, a large company in solid-state lighting. Next to him is Mike Krames, the CTO of a smaller but growing company, Sora, also in solid-state lighting. And then Kelly Gordon from a national laboratory. She's a program manager at Pacific Northwest National Lab. And finally, we have Steve Denbers from academia, who will talk to us about the future. So it's a good representation of a small, large industry, national labs, and academia. You can read the biography of the 4 distinguished members here. I'm not going to go through that, but each one of them has 10 minutes to give his presentation and her presentation, and then we'll leave 30 minutes for discussion, and I encourage you to write your questions. And I would recommend, if you have a question, please line up between those 2 microphones, much easier than passing the microphones. Okay, so we'll start with James.
Thank you, and thank you for inviting me and giving me a chance to talk to you today. I'm going to give sort of Cree is a big, large company, and the majority of its business right now is related to LEDs and LED lighting. So I'll sort of start us off with a snapshot of where the industry is. And this is the usual, Cree is a public company, so what this says is just be careful, take what I say with a grain of salt, and whatever you do, don't make investment decisions based on what you hear here today. Just a brief introductory slide here. Just to bring everybody on the same page, the typical white light, there's different ways to make white light with LEDs, but what's really dominating the industry right now is this approach I've shown here, is we take a blue LED chip, we add a blend of phosphors, which down converts some of the blue light to create a white spectrum. And it's all packaged in something like a little surface mount package, typically millimeters to centimeters in size. And you can see the reason this has sort of become the industry workhorse is it's got that what we really need for lighting, which is relatively easy to manufacture, and you can really tune the white output to the particular application. Lighting is a very diverse market, so it's no good having one device that will try to serve them all. You really have to tailor the device. And see here just some spectra where you take different amounts of blue, different amounts of phosphor, yellow, reds, and green phosphors in the blend to get the different whites. And in some cases, you can build up some more sophisticated level color spectra at the system level by combining sort of yellow LEDs or these white LEDs with red LEDs, and that's that bottom one. So I'll just give you a brief, this is where it's sort of snapshot of where we're at right now. There's been some rapid progress I'll talk about a little bit later, but what you see in the top left here, industry has sort of coalesced around 2 or 3 sort of basic chip designs. These are the blue LED chips shown here. Sort of basic technology platforms, thin chips that just emit in a 2-dimensional layer, to transparent contact chips, and then flip chips, which sort of the large one on the top left there is a flip chip. That's a faceted silicon carbide substrate you can see there. And then so these basic technologies have proliferated into different sizes depending on the final application. And then there's also, again, to sort of go along with the chips, there's 2 or 3 different basic approaches to incorporate the phosphor in a wide variety of package types, just depending on the final application. So this is sort of top production performance currently. Top white LEDs. This is actually that large faceted chip on the top left. This is a typical package for that. It's a 1 millimeter die in a 3.5 millimeter package. This sort of leads the pack just a little bit. They all end up, all these different technologies, right, if you do it right, they all end up with about the same efficacy right now for a given input quality material and a given output spectra you're trying to achieve. So what you see there in the graph is the efficacy we can achieve as a function of input power. And for different whites. So there's just 3 different curves there from a cool white, sort of daylight through the warm whites you see sort of at your home. And so what you can see there, so this is efficacy at an elevated temperature around 85 degrees C. This is sort of typical for a lighting application, give or take. So these are sort of realistically what you can achieve out of a white LED component. You can see there the peak is we're getting up close to the sort of the 200 lumens per watt with the cool white, 180 lumens per watt, and then it falls off. But what's key is right now is you can get working devices, you can buy product well in excess of 100 lumens per watt, which is sort of a real nice threshold in terms of allowing you to do things and really challenge the incumbent lighting technologies. So one of the things you see here is the droop, the fall off in efficacy is a function of input power density. You hear about more from this from Mike, no doubt, and probably Steve. A few years ago, when we were sort of down at the 50 lumen per watt level, this was a real problem. If you can barely get to 50 lumens per watt and then you lose a third or half of it as you go to higher power densities, that's a real issue. But now the peak efficiencies are well above this 100 lumens per watt. This droop has become less of an issue in terms of getting in the way of making real useful lighting systems that can compete in the marketplace. So this is just a snapshot of, this shows the rapid progress over the last few years. I don't know how often you've been exposed to solid state lighting. If your information is more than a couple of years old, it really is out of date. This is a fast-moving industry, and you can see in 2 ways. The efficacy curves the efficacy you can achieve out of white component has gone up by sort of almost a factor of 3 since 2005, when sort of the first lighting class LEDs first came out. That's a fairly rapid trend. It should continue, hopefully, for a little bit longer. What's more important, though, I would argue, for really getting solid-state lighting growing and getting it to the end user is the cost at which you can achieve the sort of 100 lumen per watt benchmark level. And that is the blue curve, and that has dropped a lot more. That's dropped sort of like the factor of 10 is what it costs you at the LED component level just to achieve some number of lumens at 100 lumens per watt. And that's what's really been driving the adoption over the last couple of years. And so I'm just going to give you a real-life example. So 2008, this is for an architectural troffer. This is sort of be your, think fluorescent tubes fixtures in a industrial office setting kind of thing, right? So something where it's got to be reasonably high quality light, several thousand lumens, few thousand lumens, typically in the ceiling, right? So in 2008, we were able to put out a product that was getting sort of 65 lumens per watt, 90 CRI, which is a measure of the color quality, so it's a very nice, pleasing light, much better than what you typically get from a fluorescent fixture. This thing was sort of, we had to throw a ton of LEDs at it just to get to that level. And you can see the picture at the bottom left there. It's just a sea of LEDs just to get enough power or enough efficiency. And then, well, you have a lot of LEDs. They do heat up, so you have to have a large heat sink. So that's what that big black thing in the bottom right picture is. It's basically a fairly large chunk of metal to take the heat out of the back of the part. So all up, this is about $400 is what it would cost you to buy one of these. With those efficacy gains that have been so rapid and the cost gains that have been so rapid the last few years, we've really been able to drastically change the values. So this is the sort of a next generation device we call CR22. It's basically the same product. It looks different in the end because what we've done, once you have these very different or much more higher performing LEDs, you need a lot fewer of them. You need a lot, your heat sinking gets a lot different. You can basically redesign the system from the ground up to take advantage of these much more efficient devices. So it ends up looking different. To the end customer, it gives them what they want. It's exactly the same thing. So 3,200 lumens, 90 CRI. So this is now 100 lumens per watt. I mean, this is a product. You can buy this. It uses about 30 LEDs, and they're just arranged in a strip there. You can see that in the bottom left picture. Just a central strip of LEDs that sits on a heat sink, very small heat sink, gives them enough heat sinking capability to maintain the lifetime. And this now only costs about $159. So, I mean, that's a pretty large drop in the price. But what's critical for the adoption is now the payback. And I have to admit, Claude Weisbuch has started quizzing me on payback, and I haven't actually gone through the calculator, so I'm having to trust my marketing department here. So bear with me. When you take into account the energy gains, the replacement costs, the initial costs, compared to the fluorescent architectural troffer this is supposed to replace, you're now getting down to where the payback or the return on investment is less than a year. That is a very easy sell. All right? Anybody who is looking at their budget, running a building, they are going to pick this up, and they are. So this technology gains at the component level is really showing up all the way through the system level. I'll skip that. So that was just one example. That's a troffer. There's a huge number of other applications where it's a similar story, where you have this, this rapid drop in the cost of achieving what you need as the end goal. So there's a lot of adoption. We're still at the early stages. I did want to touch on the light bulb here because people understand the light bulb, right? You get to see this. This is what you pick up at the Home Depot. Nobody goes and buys a troffer. I mean, regular people don't go out and buy a troffer and reinstall it in their home, right? So the light bulb. How close are we to that? And if you had to design a fixture which was less suited for LEDs, good luck, because trying to replace the incandescent, it's apart from its low efficiency, it's got great light, or for lifetime. Right, but it's very small, and you've got to get lighting going all directions. That is a tough nut to crack with the LEDs, and it's very low cost, right? So you go into the. Yep. So I think we're there, just about. You can tell me. So this is the shameless Cree plug. This is a new light bulb, and it just came out like a month ago. And the key thing here is I think we finally got it down to where the value proposition is getting there. So it's a $10 light bulb at the Home Depot for 40 watt equivalent, $13 for a 60 watt equivalent. My wife's not running out to go buy these yet, so I'm not sure the value argument is quite there, but it's pretty close. And this is really, still a complicated system compared to the, where it has to get to, but it's getting there value-wise. So, and I will leave this because I'm out of time. Go to the next one. Thank you.
Hello, I'm Mike Crames, Chief Technology Officer at Sora. Just a word about Sora. We're actually founded from founders from University of California, Santa Barbara, including Shuji Nakamura, who invented the blue LED, and Steve Denbar here is on the panel with me. So we have strong ties to Santa Barbara that we're very fond of. I have just two concepts that I want to try to convey. Thanks to James for laying the landscape, and I think it's clear that Cree's done a great job in establishing leadership in the U.S. and where LEDs can go today. But we see opportunity beyond where even Cree is today in terms of cost reduction and also addressing certain quality of light aspects that are there today, even with LEDs, that we think need to be addressed for mass adoption. So those are the two main topics I want to mention today. When we talk about cost, well, actually, let me, I guess, start with kind of the basic of the technology. So what is LED 2.0? LED 1.0 is the first generation of LEDs based on Shuji Nakamura's invention back in the 90s at Nichia Chemical Company, and that was related to the fact that you could grow gallium nitride on foreign materials like sapphire. All the other 3-5 semiconductors had substrates that you could grow from the melt, and that was also true for silicon, by the way. So you had substrate technology available, so you could grow lattice match structures where the atoms would go in the right places, and you could grow very defect-free material, which is required for a semiconductor that's going to have a band gap. And so the notion that you could grow a single-phase material on a foreign substrate was a radical one, and it really ushered in the first era of technology up till this day. And that's true also for the results that James talked about. In their case, the foreign substrate silicon carbide. But you still have the issue that the material is defected. And this puts limitations in terms of the reliability, in terms of the power density that's capable. And so with the LED 2.0 or GaN-on-GaN approach, that, as we call it, we are putting the active device layers directly on their native substrate. So the dislocation densities or defect densities are reduced by several orders of magnitude, and that allows us to basically operate the LEDs at much higher power densities. That gives us higher brightness, higher luminosity in applications, smaller chips, and there's also a cost impact, and that's kind of shown and has a good analogy to Moore's Law. So if you think about Moore's Law, there's a couple different ways to think about it. One is transistor count, so more functionality in the chip. Another way to think about it is in terms of transistor density or the size of the chips, the number of chips per wafer. At the end of the day, an IC manufacturer wants to sell more chips, not necessarily more, once a functionality is at a certain level, you want to sell more chips. That's the main thing, and a higher density of chips allows you to do that. We have the same opportunity with LEDs. If you look at now lumen density, and this is developed after observation that Roland Heitz had back at HP. I think Wagi mentioned Roland earlier in this early solid-state lighting white paper in the 90s. There seemed to be this progression of lumen density as a function of time. And what we've seen, though, in the last few years is that improvement begins to be slowing. And in order to get more lumens out in these large lighting applications where you need thousands of lumens, people are putting more and more chips in. And I think you could see that in some of the slides that we just saw. And so you actually see things going the other way. The lumen density is going down. And the reason that that's happening has to do with these limitations that I talked about in the materials. It has to do with the LED droop phenomenon, which is, as we know and is confirmed now, is Auger recombination. There's an interesting history there, and I'll leave it to Steve to tell you about that history. But just throwing more chips at the solutions to get more light output and maintain efficacy, we think is fundamentally not the long-term way to go for cost reduction, reducing the use of rare earth materials, reducing the use of the amount of electronic waste. So there's an opportunity to do something better. And with GaN-on-GaN technology in this data point here at about 250 lumen per square millimeter is where our first generation technology launched last year put us. By having a GaN based LED platform, we're able to operate in a completely different regime and continue to push lumen density forward without sacrificing efficacy. Our Gen 2 products that we just announced last week have a 50% higher number than what I'm showing here. So we see this as a way to fundamentally drop the cost of manufacturing the LEDs. Again, what matters in a semiconductor fab is when you have one lot of wafers going through, what we sell is lumens. So it's the lumen density of the wafers that matter. It's not anything else. That's the main thing. So that's our perspective on cost. These are the products that we have right now. You know, again, small startup. We have a first line of products. They're built around the MR16 lamp. You're probably familiar with them if you've looked in hotels and restaurants. You'll see these low voltage lamps. The sweet spot of the halogen devices that we're replacing is around 50 watt equivalents. We're actually able to achieve up to 75 watt equivalents with our LEDs, and absolutely no compromise in the spectrum. And I'll talk about that a little bit more here. Very happy with the market acceptance. We've got a number of awards on the design and look. We have a real side-by-side compared to halogen. You would not know it's different in terms of the color quality, except that it puts out a lot less heat and saves you 80 to 85% of the energy. So it's very compelling. And the payback for these lamps is as James said, this 1 year payback is a real critical period. That's true for these lamps as well. The other barrier to adoption, in addition to cost, we believe is quality, and we have no further to look than with compact fluorescence to see how not to do that, okay? So we've had energy efficient technology for more than 20 years at our disposal with compact fluorescence, and we could have been putting those into our homes. At the end of the day, up till now, the penetration is on the order of 15% or so, depending on what report you look at. By far, this is not success. And if you, McKinsey, this is the table that I adopted here from their report on lighting the way. They interviewed people across all different segments, you know, residential, office, industrial, shop, hospitality, and architectural. You ask people what they care about. Quality, like quality, is number one. The only exception was in the residential where price and quality were kind of on par. But the bottom line is that we've grown up and evolved with light in the case of natural light, you know, millions of years evolution, and at least with incandescent light, over 100 years. Everybody, to some extent, is an expert in lighting and wants light to look a certain way. And the bottom line is with CFLs, we didn't get that. We got weird colors, we got warm up, time where colors changed as the lamps were turned on and turned off, and other, you know, of course, there were other aspects like reliability. Of course, they're poisonous, right? These other kinds of things are issues. And the exciting thing here is that we know all that, so why on earth are we going to do it again? And we don't have to do it again, but we have to think about these other aspects: color uniformity, color rendering, whiteness rendering, which may seem like a new topic, but for most of us, I guess it is, but I'll talk on that. The beam quality, dimmability, and the environmental aspects are all critical factors we have to keep in mind as well. So how is Sora doing this? In terms of color quality, we are the only LED company that makes end products that use the full visible spectrum. So we actually put enough energy into the LEDs to start with 3 electron volts energy, so violet, and pump a cascade of phosphors to get the entire visible spectrum. So we go all the way, there's no UV, we start right at the violet, all the way to the deep red, they get very, very high color rendering, and then there's no infrared whatsoever. We think that's about the best you can do, and that's what we call it. Our marketing guys, anyway, call it the perfect spectrum. So we get the best of what you would have with daylight or with incandescence, but with none of the bad stuff, no UV, no IR. And we do much better than the blue-based LEDs. So visible spectrum starts in violet, not in the blue. If you start in the blue, you're missing that first violet part, And because of the Stokes gap between blue emission and phosphors, you also end up with a little gap in the cyan for most LEDs. And that's true for 99% of the LEDs out there today. You have this broken spectrum with no violet and a gap in the cyan. And for reference, there's other cartoons of spectra out there too, ceramic metal halide and compact fluorescent, which is even worse, just narrow spikes of light. At the end of the day, these sources do not render materials naturally. Not only in terms of color rendering, but also in terms of textured materials and other things. And I don't have time to get into all of that. You'll see more of that as we develop this technology over the coming years. But one aspect I'd like to bring up, because it's such an obvious one, or at least it seems obvious, but it surprises people every time that we bring it up. At the Light Fair booth last week, we had a Sora MR16 and a competitor lamp up, just looking at white materials, cotton t-shirt, a white mouse, and white earbud phones from a California-based computer company. And in the one case you look at, under the Sora lamp, you have this vibrant, white appearance of the materials. And in the competitor, big lighting company lamp, the stuff looks yellow. And the reason it looks yellow is that most manufactured white goods have, over the decades, been incorporating optical brighteners. And that's true for cosmetics, paper, clothing, the tablecloths here, my shirt, this pen. A lot of stuff has these optical brighteners, and they've been engineered over time to really give you that crisp white appearance when illuminated by broadband spectral emission, whether it's daylight or halogen. And so at Sora, we started talking to retailers who were missing something, and we realized this is what they're missing. We've dialed in the violet emission from our LEDs to be able to really nail this whiteness aspect. And I raise it because it's on par with color rendering in terms of being important for rendering materials the way we all expect they should be rendered. So you can't imagine a retail store with white clothing where during the day everything looks great and white, and then at nighttime they turn yellow, right? That's absolutely not acceptable. So these are exactly the kinds of things that we need to have eyes wide open about as we go forward with LED technology. And Sora's job, as we see it, is to provide that path, absolutely no compromise on both color rendering, whiteness rendering, all the other qualities of the lighting aspect you want, and with a long-term entitlement to fundamentally lower cost at the semiconductor level. And so those are my two thoughts.
Program. She's a manager of the solid-state lighting program. She'll talk about key performance attributes and metrics for solid-state lighting market adoption.
Thank you very much. I'm Kelly Gordon. I'm with Pacific Northwest National Laboratory, and we provide the lead technical support to the DOE solid-state lighting program. I'm very happy to be with you here to talk about SSL market adoption. I think we've heard about how quickly LED technology is advancing and how much it has come so far. And you could get the idea that LEDs are everywhere. We're starting to see them in many more applications. We were at Light Fair in Philadelphia last week, and pretty much all you see is LED there. But the reality is that we're still at relatively low levels of market penetration for this technology in the lighting market. DOE just published a report on LED market adoption, and for 9 different product categories, and most of them are less than 1% of the market. The top one is MR16 reflector lamps, which are at about 10%. So why isn't it higher at this point? What are the hang-ups? I'm going to talk about several, and obviously there are many things going on here in the marketplace, but these are 3 key areas I want to touch on. The first is product variability. It's still a very dynamic stage of the development of this technology. These are by no means commodity products. They are individual, need to be individually evaluated. Controls is a really hot topic in our industry right now in lighting. And LEDs open up, as a solid-state technology, they open up a world of control that we have never known in lighting before. And that has tremendous opportunities in it and tremendous challenges. We're putting a new technology on top of the existing infrastructure in our buildings and our homes. And then, of course, there's the cost and value propositions. So let's talk about performance variability. This is just one example. This has to do with luminous efficacy, the amount of light that you're getting out of LED products for each watt of energy going in. And this is based on the DOE LED Lighting Facts database, which has more than 7,000 products in it now. And it started back in the third quarter of 2009. You can see the average efficacy at that point was 38 lumens per watt. Now, as of the first quarter of 13, we're up to 72 average. But also look at those whiskers, the tails, the max and min. There is huge variability. We've got a couple of products in that database now that have photometric reports indicating they have 140 lumens per watt, 170 lumens per watt. Very high, but the bottom is still at the levels of say, incandescent light sources. And this is just one area where there's great variability in the products. Color characteristics, lifetime and reliability, dimming performance. There's variability in all of those areas. So what are people to do when there's such great variability and you can't tell, is an LED product going to be good or bad? You have to get the facts. You have to do some homework and some legwork usually. Fortunately, there's a growing number of resources that are available to help out with that. The Department of Energy does offer a number of them, including the Lighting Facts program, gateway demonstrations, caliper testing. We do a lot of the testing in-house. We also work with testing laboratories and make that information public so that you can sort the wheat from the chaff. There's also the Energy Star program, design lights, and an increasing capability of the manufacturers to know and report using industry standards. Now in the controls area, as I said, huge area of potential. We'll be able to do things with lighting that we've never been able to do before. But it's going to take some time to get there because controls are not easy to implement. And in the lighting industry, we laugh about this because it should be easier. But just something as simple as dimming. And here in California, starting next year, commercial buildings, light sources will all have to be dimmable. So this is a serious issue. It could have serious implications. This is one example of some LED troffer fixtures, the kind that go in your office, and the flicker waveform. So what is the light output doing when the dimmer is at 100%? There's no visible flicker. It's just at a steady level. When you move that dimmer switch down to 75% for this particular fixture, you start to see the light output going up and down. And at this frequency, at this level, this would be detectable by many people. So that can be a problem. There are standards efforts working to overcome some of these issues. NEMA just published SSL 7, or the first part of it, which will be an interface standard that addresses this interaction between dimmer switches and LED light sources. So it provides some design criteria. And that is an incremental step. Standards obviously take a long time to happen, but this is one step in the process that will help. There are also non-standards approaches that we can take, and one example is DOE's model specification for adaptive control for LED roadway lighting. This is really aimed at municipalities and utilities and others that run street lighting systems on how to spec control systems. It's not an industry standard, it's not required, but it is a consensus specification, so cities can use this document when they go to spec out a system, and they can modify it as needed. And then finally, cost and value. We've been talking about how the costs are coming down, and they certainly are. But in most cases, LED products are quite a bit more expensive than traditional light sources. But this is one example. This is from the city of Seattle. They've been implementing a multi-year program of purchasing LED streetlights and changing out the streetlights in the city. So over the past 4 years, they've been seeing significant decreases in the prices, per unit prices for large volume purchases. That's about 17 or 18% average per year that those are coming down. And then to loop back to controls in this in this cost scenario, controls can be a real value added to LED systems. And LED, because it is a solid-state technology, is inherently more controllable than traditional light sources. With high-intensity discharge sources especially, you can't put them on an occupancy sensor normally because there's a restrike time. You know, when it goes off, you got to wait for it to cool down before you can strike it again to turn it on. And this was the problem at the Super Bowl, right? The lights went out and they had to wait, because if they'd had LED, they could have brought them right back up. So the controls can help the cost and the value proposition with LED lighting. This is an example from a parking garage. This was a gateway demonstration project at the Department of Labor in DC. We changed out the high-pressure sodium lighting in the parking garage to LED, and that alone dropped the energy use by 50%. While maintaining the necessary light levels. But then the addition of occupancy sensor controls decreased that further, and then fine-tuning the controls so that it was really tuned to the way that garage was used and adjusting the time delay yielded a total of 89% energy savings. So it can make a big difference, and it's because of this enabling technology that it is inherently controllable. That makes a better story and a better proposition. And it should lead to better lighting services and potentially other services. The integration of controls with, say, responsiveness to the electrical grid, integration with emergency systems. We'll be able to get more information from our lighting systems than we've ever been able to do so before. It won't be just a light sitting there. It will be doing something useful. And I'm going to stop there a little bit early. Thank you.
And our last speaker is Professor Dan Burns, who will talk to us about a glimpse of future solid-state lighting.
Thanks, Woogie, and thanks, John and Dave, for organizing such a wonderful conference. So I'll talk to you a little bit about what I see as the future directions of solid-state lighting. Been in the industry 20 years and seeing it finally get to lighting is quite exciting. So I'm going to go out a little bit on a limb here and just say that I think that we're going to see lighting revolutionized from the simple light bulb into complete communication systems that potentially you could do internet over, but also systems that you can control and actually improve your health because of things like seasonal affective disorder or other things, or just sleep disorders. It turns out Alzheimer's patients, if you irradiate them with blue light during the daytime, they can actually sleep better at night. So there's going to be a real revolution here. So starting with, let's see if this pointer works over here. Yeah. With the new chip designs, I think you're going to see companies like Cree and Sora continue to make new designs. Cree has a very innovative chip on silicon carbide where they use it for high light extraction. Mike mentioned the gallium nitride substrates. Both of these offer advantages for different products. One's for MR16 and one's more for light bulbs, 60 watt that is. I think we're going to see the efficiency droop being solved in our lifetime, hopefully. And some of my colleagues have recently further concluded and elucidated the mechanism of droop, which was actually first proposed by Mike Crames at Lumileds, and I'll show you a view graph on that. And so what we've seen over this past 10 years is the lumen density keeps increasing and increasing, and you need less chips, but also the size of the lighting system is being reduced. One example of this is that I'll mention is the projector bulb, which is going from basically metal halide based to laser based, and the size of the projector is being reduced, hopefully to the size of your cell phone someday. I think you're going to start to see intelligent LED lighting systems, and Kelly alluded to this, and I think this is going to be one area for huge growth opportunities, both for services, but basically being able to completely control the color of your light bulb and the hue, but also building communication networks. You know, we'll be able to sell you a light bulb maybe for the same price or a few cents more that also can communicate at about a gigabit per second. So this would have enormous, added features to the lighting. And like I said, you could have it be adjustable, or like she said, have it on motion sensors. You can imagine street lights, which only turn on when there's a car approaching. This would save enormous amounts of energy in some of the street lighting in highways that doesn't need to be on all the time. Finally, I think one of the little bit more farther out ideas I've been having and trying to convince people is that I think laser lighting, in which you down convert the laser light to white, has the opportunity to completely revolutionize lighting by being distributed over fiber optics or being fixtureless lighting. That is, the size reduction afforded by a laser lets you really rethink what kind of lighting you can do. So I'll touch a little bit on these. First, let's talk about the intelligent LED light system. So here's a little cartoon I took from off the web, but I thought it kind of portrayed what I really foresee lighting as being in the future, is that you'll have light bulbs that can communicate with your iPhone or your computer. You can have them be on sensor or alarm, so you can see basically, you could have a social preference. Let's say some people like a really cold lighting, which is considered about 6,500 Kelvin. It turns out people in the Western world here, we prefer warm white, it's called. And so when you come in the room, the lighting might change to your color preference, which you could have encrypted on your PDA or cell phone. You could even think of doing fairly high-speed networks. And this doesn't even have to be direct line of sight. We did some early studies on this at Hewlett-Packard. It was over 20 years ago. And you can do about 4 bounces off a wall. So you could have a light bulb in this room being communicated with somebody as long as it's only about 4 wall bounces away. So I think we're going to see lots of opportunity in basically reinventing the light bulb. It's not just about light anymore. Some of the future trends that is going on right now, and I see is continuing, James mentioned the dominant workhorse here is where you take a blue LED light and you down convert it with yellow and red phosphors. This currently dominates the market because it's the lowest cost, and it also gives you the best efficiency. However, Mike had mentioned a violet pump, pumping 3 phosphors, can give you the best light quality and consistency at a reasonable cost, and particularly for the MR16 or the directional light, shows some advantages. And then I think the red, green, blue LED affords you the ability of complete color tunability, and actually all 3 of these can be communication enabled. So there's going to be, I think, a lot of research going on how to increase the data rate speeds and even setting up what kind of standards we need to do there. Just like to put in one plug here for one thing that both the university's done, but also on the theory of droop. This is what causes that efficiency drop that James and had mentioned at the first, why we can't get a single LED to put out a lot more light. And it was initially actually proposed by Mike Krames here when he was at LumaLEDs in 2007. It took us basically 6 years to actually get the experimental verification of this droop mechanism, and then further refined the theory by Chris Vanderwall about 2 years ago. So this was just announced last week by Jim Speck and Claude Weisbush, where the electrons, rather than give off light when you put electricity in it, it basically gives off additional electron, which then gives off heat, which causes the efficiency to drop. So now that we understand the fundamental mechanism, I think many groups around the world are going to be working hard to solve this with various different chip schemes. Some other new technologies that promise further improvements in efficiency and also cost reduction. Photonic crystals have always theoretically shown the promise of having very high efficiency in terms of light extraction. We continue to work on this with Claude and groups around the world on trying to get higher light extraction. Pure bulk gallium nitride, in which we actually slice the crystals at different crystal planes, show great promise in helping us solve the droop issue. And we're applying many of the cost reduction techniques that, like Stephen Chu said, if you find a cheaper way to make bulk gallium nitride, everybody would switch to this overnight. However, today it's expensive, but we're envisioning, and we've demonstrated some new techniques to make this process cheaper. So that holds great potential for future research directions. And then thirdly, I touched a little bit on the laser diode work. This has great promise, I think, for directional lighting, and this is actually a mock-up from a BMW motor company has done that says that this would reduce the size of the car headlight to extremely small because it gives you a truly point source. And what they have here is there's a phosphor disc in the middle here, and they're hitting it with a blue laser. So you're not going to be blinded by these headlights, it turns out, because it's converted into the white light. But it's extremely directional because you have such a nice point source, and it's already at 80 lumens per watt, which is very early stage for the laser, because the laser is not as efficient as the LED to date, but 80 lumens per watt is pretty decent. It's actually better than the halogen it's replacing, which is about 30 lumens per watt. And like I said, several automobile companies around the world are now working on this. So you'd have very small headlights in the front of your car. That would reduce the space needed for the lighting system. So this is kind of what I've envisioned as some of the future work that we have to do. And again, one of the things that make this so small is it basically is 1/100th of the size of the traditional power LED chip. Other places, you can actually buy a laser diode-based display system today. It's the Casio projector. This just shows the optics. They use a blue laser here to pump a green phosphor wheel, and they actually combine that with a red LED. This has let them shrink the projector down to about half the size of the one that's shown in this room. Actually, it's much smaller than that one. That's an old style one. And then there's work going on at Sandia Labs where Jeff Zhao has been a proponent of actually using not just the phosphor converted, but actually using 4-color lasers to display certain things, and they actually get very good color rendering, which is actually quite surprising to me. So I'd like to conclude in the last minute of my talk by talking a little bit about what the National Research Council has just came out about 3 months ago with their recommendations for funding for solid-state lighting, but where this is a panel I helped serve on with about 14 other members, and it kind of hits on some of the points that the speakers have mentioned. The first one I think Kelly mentioned is dimmability is still not quite there with the LED lighting. You have to go kind of dimmer by dimmer because certain people have different drivers and dimming functions in their room. So there needs to be better standards set up for dimmer controls for the LED. But then you look, a lot of the basic recommendations from the NRC, I want to emphasize, basically came back to basic material science issues where they want to see funding of the processes, the crystal growth technique to use LED manufacturers is a very complex oven, I call it, an MOCVD process where they more monitors and better uniformity will give us much better cost reduction. Development in new materials for substrates, particularly gallium nitride substrates. They want to see continued investments in the core technology. And this is actually, since I've got the podium, I can say a little bit about it. Core technology only gets about $20 million in federal research dollars a year. And countries like Korea and China are investing on the orders of hundreds of millions in this area because it's deemed of significant importance for the economy. So that's one area where I personally would like to see more research spent is on some of the core fundamental materials research. And then finally, DOE has been guiding this program for over 12 years. And I just want to, the recommendation was to make sure that they cover an extensive amount of materials and devices that we can continue to deliver lower cost LED lighting and make it affordable for everybody so that we can switch over to LED lighting, which I foresee happening in the next 5 years. And I think Jeff Henley, I just want to last plug, Jeff said he believes by 2020, 100% of all the lighting will be LED. So I hope he's right. Thanks.
I don't believe it. It's 41 minutes. That's nice. So you kept on time. And we're open it for questions. So if you have questions, please line up here on those two, behind those two microphones. And I'll just get the group started with one question that has been bothering me, actually, despite the progress that you described. And Kelly mentioned some of the issues that are standing in the way of wide deployment and having this technology being very pervasive. Very quickly, in 1 minute each, what is it that you think is really the reason for why it's taking longer? I mean, every technology takes really longer than expected, and I hope that Jeff is correct in his 2020 prediction. But what's stopping from having lights everywhere as LEDs? James, your 1 minute.
Okay. I think it's certainly one thing is it's only recently where the efficiency has really got to where it needs to be on a manufacturable basis. So maybe the last couple of years, where you can. So what we end up doing is you create a lot of lumens at the package level, and then you tend to throw a bunch of it away as you, or at least energy away as you build it up into the system. So we needed some headroom that the components are now offering, and now that that's there, I think it's really it's rolling things out. It just takes time to manufacture. It's not like there's 3 kinds of light bulbs, right, that you just replace. There are hundreds. And so It just takes time to choose them, go through all the engineering cycles, to roll them out, and there's sales teams associated with it. So it's just a sort of knocking them off one by one now, I think. And so I think it is happening now. So come back in 2 years, I think you'll have a different perspective. So.
I think that's right. It does take time, even when you have everything. We saw this with the LCD backlighting industry, who kept saying win, win, win. And then once you got past that knee in the S-curve, it just happened overnight, and then everything was LEDs. So it's going to be a little bit different than that because it is a fragmented market, as James pointed out. But obviously, costs have to come down. And I think there's also a quality, as I mentioned, a quality aspect. People, at least at the residential consumer level, have been burned in the past. And they're going to be hesitant, I think, to jump into something unless they really have that assurance that the quality is going to be there and the expected lifetime is actually going to be there as well.
Kelly, you want to add to what you said?
I would agree with what they said. And it's just a very dynamic time still, and the products are changing so rapidly, and there are still gaps. So now you can get pretty good 60-watt replacement lamps if you go to Home Depot. But a lot of people want 100-watt replacement. That's much harder to do, and it's much more expensive. So it takes time for that all to work through and to get to prices that truly are competitive.
Thank you.
Okay, I'll just say, I think the reason why it took so long primarily was the cost, performance, quality. These three things didn't coalesce until, I'd say, just in the last year. So we didn't have the cost. For instance, just 2 years ago, it was $40 for a 60-watt light bulb. Now you can get it for $10 or $12.97, I guess, James. But the quality wasn't there. Everybody was complaining it was this bluish white. So now we've got the quality. And then the final remaining thing was the performance. The efficiency wasn't better than compact fluorescent. It was, let's say, a few years ago, it was 40, 50 lumen per watt. Now we have 80, 90 lumens per watt. So we beat compact fluorescent. And then in R&D, people are talking about 200 lumens per watt. So now we're beating fluorescent in the R&D stage. It'll still take a little while to get that into the product. But yeah, so it's been those three things holding it back, and we can see the light at the end of the tunnel, so to speak.
Very good. Okay, let's see. Name and affiliation, please.
Yes, my name is Thomas Dittler. I'm here with the Band of Angels. Would you please give us some insights into the question of life expectancy, the improvements in life cycle, costing, and also in life cycle duration in terms of years? And also, what kind of testing regimes have you developed to help with accelerated aging and really test 25,000 or 40,000 or 50,000 hours of life expectancy? Thank you.
Let's start
That's
with
to the whole panel, actually, because nobody of you really touched on life expectancy. Thanks.
Let's start with industry first. Yeah, go ahead.
Speak to that. So we take a page, we're semiconductor based, all of us in the LED industry, and we take a page from the telecom industry in terms of accelerated life. So the two things you commonly push are power density and temperature. And you basically run the parts at ranges of temperatures, ranges of power densities, and by using standard Weibull distribution type analysis, you can thereby get acceleration factors and predict life. That's pretty straightforward. You can do the same thing with the electronics, and those have to be done as well if you have a system product. Sometimes you can be surprised. Usually you're surprised by the things that you assume they're going to be fine, and you find out that they're not. That maybe standard things in assembly. But I think the basic rubric we all go through for lifetime is pretty well understood, and almost everybody does it the same way. In terms of target life cycles, I'll go out on a limb and say that really long lifetimes are nuts for any kind of lighting product because they in fact lock you into energy inefficient technology. And if you look at the MYPP roadmap that the DOE publishes and calculate an optimum lifetime for an SSL product to minimize energy consumption over the next 20 years, is about a 10,000 hour life. It's not even the 25,000 that's rated today. So going to 50,000, 100,000 hours is, I think, the wrong way to go because it puts all the burden on the manufacturers to make more expensive products that take longer to release. So it would actually make sense to go the other way. But there is this kind of emotional attachment right now to 25,000 hours, even though in a residential application, that's about 20 years today. which is silly.
James, you want to add to that?
Yeah, that there's sort of this dichotomy. If you, I mean, I agree with Mike. I mean, you really don't want to lock people in, but on the other hand, they've got to put out a lot of money to switch over, right? So there's this, okay, how soon am I going to have to replace this new bulb? I'm spending millions of dollars refitting my building. I want to know it's going to last a long time. So it's an irrational response, but it's a real human response, right? Is they want to know it's going to last. I think that's what's sort of driving I mean, Cree's right now got this push rightly around the 10-year warranty, right? I mean, so the hours is 25,000 to 50,000 hours, depending on what the application is. But that seems to be sort of a comfort zone for people who are forking out the money. So it may be heading in the wrong direction from a long-term energy savings, but that seems to be what is helping to sell product right now.
Any other comments?
Different market segments are going to have different considerations for lifetime, too. I was thinking about the residential segment for most of my comments, but I think James would have to agree that if you're designing a product for a 10,000-hour life versus a 10-year life, you're able to make some choices that would affect the cost of the product. And you could have cheaper products that would be adopted more quickly and realize energy efficiency benefits more quickly, which I think is what the DOE would like to see.
I think there was maybe a tendency, especially at the beginning, when yes, LEDs were a lot more expensive, and so the argument to be made was, yeah, but they're going to last a really long time, and it's almost like we boxed ourselves in with that, putting everything on that argument that it's all about lifetime. Now, and so I think that will change because it'll be more fine-tuned to the particular application, what makes sense, and allowing for people to be able to change it, to upgrade to the next best thing. Now, the other aspect of this whole life issue is that there are not good industry standard test procedures yet for life. There's a lumen maintenance test procedure, but that is only a small part of the life and reliability issue. So the industry may know kind of how to test and project their own, make their own life projections, but there are not good standards in that sense yet. So from the lighting community, they take all projections, I think, with a grain of salt until there is a common industry standard life testing procedure, which hopefully will happen relatively soon.
Is anyone trying to do that? Is Department of Energy?
Yes, the IES Test Procedures Committee is working on several different aspects of that.
Okay, very good.